All right, hello everyone. I'm Norman Wildberger. We're here at the University of New South Wales. Today in this course on differential geometry, we're going to investigate a little bit further the role of projective geometry in understanding two-dimensional and three-dimensional space. So projective geometry is not so much studied subject these days, although 100 years ago it was very much more studied. But it's a very important tool, a very powerful tool to help us with a lot of two-dimensional and three-dimensional problems. In fact, it has a major role to play in graphics and in computer work in 2 dimensions and 3 dimensions. So last time we were talking about homogeneous equations for various simple curves. And let's just have a look at the general case of a conic. So a general conic in the usual xy plane has form something like ax squared plus, say, I might write 2dxy plus by squared plus 2fx plus 2gy plus c equals 0. That might appear sort of strange choice of coefficients, but you'll see in a second why that's the case. So this is the general formula. That's the general case in the affine plane, and from the affine xy plane. Okay, so the corresponding projective object or the corresponding projective curve is obtained by replacing the little x with capital X over capital Z and the little y with capital Y over capital Z. So a capital X over capital Z squared plus 2d x over z y over z plus b y over z squared plus 2f x over z plus 2gy over z plus cz plus c just by itself equals 0. Which we can rewrite in a better way by clearing the denominators, multiplying by z squared. So we get a capital X squared plus b capital Y squared plus c capital Z squared plus 2d xy plus 2f xz plus 2g yz equals 0. So basically what happens is that each of these terms gets multiplied by an appropriate power of z to make them all of degree 2. This is a homogeneous quadratic expression. Homogeneous meaning that all the terms have the same degree, and it's obviously quadratic. And we can write it in matrix kind of form by writing x, y, z times the matrix A, B, C, D, D, F, F, G, G times x, y, z equals 0. So more compactly, it's of the form, say, P, A, P transpose equals 0, where this matrix A is a general 3 by 3 symmetric matrix. That means that its transpose is equal to itself. All right, so this is interesting that now the general conic has been sort of reformulated to be associated with a general symmetric 3 by 3 matrix. Okay, and the picture that we have is that we're working in capital X, capital Y, capital Z space. That the Z equals 1 plane is our standard viewing plane with little x and little y coordinates. Now, whatever conic we were considering, maybe some ellipse in some general position, that two-dimensional conic is now replaced by a surface. This is defining a surface in three-dimensional space, which is homogeneous, which means it's invariant under scaling, so it's like a cone. So the surface is what you get by joining, essentially, all the points of that ellipse with the origin, and you get this three-dimensional surface, which has a sort of a cone-like aspect. That's what's being described by this thing here. Okay, so this is a basic example of projective geometry, but for us, we're going to have a closer look now at the algebraic setup of this projective geometry. We're going to introduce some important ideas of how to represent points and lines. All right, so let's have a look at some, well, really what amounts to projective linear algebra. Okay, so here's our x, y, and z space again. And let's just clarify what the actual objects of this projective geometry are. All right, so the main objects are things called projective points. And sometimes we'll just write, say, p points or just points. And what these things are one-dimensional subspaces, that is lines, in our capital X, Y, Z vector space. Okay, so that's something like this. That's a projective point. And how are we going to label such a point? Well, we'll pick an actual point on it in the x, y, z space. And let me write just x, y, z. So that's actually a particular point. And then every other point on this line is a multiple of that one. So we're going to introduce the ratio x to y to z, these homogeneous coordinates for the actual projective point. So we're going to write x to y to z. But now I want to actually introduce some linear algebra. So I want to make a vector or a matrix out of this. Well, let's adopt the convention that an ordinary vector, like this one here, that vector, would be written with round brackets. Okay, so a vector is in round brackets in this setup. And what I'm going to do is I'm going to introduce square brackets. This is really a 1 by 3 matrix, but it's actually a projective matrix. What does that mean? Well, it means that by definition, x, y, z is equal to lambda x, lambda y, lambda z for any non-zero scalar lambda. So we're going to agree that when we have a matrix with square brackets, for now, that square bracket is going to represent a projective object. It means it's going to be unchanged if we multiply by a non-zero scalar. All right, so we can write this line here in this way, but we can also write it sort of in matrix form, just as the matrix x, y, z, the 1 by 3 matrix or row vector, but it's really a row projective vector, x, y, z, without any commas. Okay, but a geometry requires more than just points. We also need lines to have a real good geometry. And so what are the projective lines? The projective lines, also called p-lines or just lines, well, they're going to be two-dimensional subspaces. So two-dimensional subspaces of our x, y, z vector space. So that's just a plane through the origin. And how do we represent one of those? Well, a two-dimensional subspace of the x, y, z space is a plane which usually has coordinates, let's say maybe expression Lx plus my plus nz equals 0. That's a general equation of a plane through the origin. Okay, and we can then encode the information there instead of writing out that equation. It's really only the coefficients L, M, and N that matter. And so we're going to adopt an alternate notation. We're going to rewrite or introduce the idea of a column vector to encode that plane. So we're going to introduce a column projective matrix, just the column with entries L, M, and N. All right, so this is a 3-by-1 projective matrix. And when I say projective, it's the same as over here. The square brackets means that if we multiply all three entries by a non-zero element, we have the same object. Okay, so this is very nice now that we have points and lines now in a very symmetrical kind of situation. Let's connect it with our two-dimensional story. So remember, the two-dimensional story is really what you get when you look at everything from the plane z equals 1. So let's have a look at what these objects look like in this two-dimensional picture. All right, so in 2 dimensions, or in the planar view, so in the planar view, that what we're calling x, y, z gets associated to the ordinary two-dimensional point x over z, y over z. Of course, that's only if z is not equal to 0. What about if z equals 0? So what does x, y, 0 correspond to? This comma is meant to be there, yes. So this is now an ordinary two-dimensional planar point in ordinary xy space. Okay, what are we interpreting a projective point like this to be? Question? A point at infinity, that's right. So this is a point at infinity, which is really corresponding to a one-dimensional subspace, which is horizontal, which is in the direction of the vector xy. All right, so this is a point at infinity in the direction of the vector xy. Okay, that's good. And what about the line? If we have L, M, and N, well, we already know what that corresponds to. We've already said it here. That corresponds to the line with the equation. Well, what you get when you set z equal to 1. So L, x plus m, y plus n equals 0. Okay, now having points and lines, we can now introduce the main operations of geometry, of projective geometry. There are really two main operations, and they are meets and joins. So let's do join first. So the join is, well, if you have 2 points, A and B, the join is the line that connects them. So if we have one point A and another point B, then the line that is determined by them is called the join of A and B. And we're going to denote that line just by the product, AB. The product for us is going to represent this join operation. Okay, so suppose we have 2 points. Let's write them as A1 equals x1, y1, z1, and A2 equals x2, y2, z2. Then what is the join going to look like? All right, so to understand what's going on, we really need to go back to this 3-dimensional picture. I'm now supposing that we have 2 points, and those points really, in some sense, are lines through the origin. So imagine that this is, let me call it A1 for now, and this is A2. And I want to describe the join of those 2 points. So the join is going to be a line, or a projective line, which is really a 2-dimensional subspace. Which 2-dimensional subspace? Just the span of these 2 lines. These 2 lines, coming from the origin, they have a span. They lie in a plane. It's just the plane that's spanned by those. And what's the equation of that plane? So the plane that they form, okay, is determined by its equation. And how do we get the equation of a plane? Well, we need these 3 coefficients, L, M, and N. How do we get those? Well, from first-year linear algebra, we have to take the cross product of the two vectors, or the direction vectors of the lines. That's how you get the normal to the plane that they span. So what we need to do is we need to take a cross product between these 2 vectors. And that's going to be a line, and that's going to be then the coefficients for the line. So we should write it in terms of a column projective matrix. And can we write down the cross product? So imagine the determinant of this with one row and this in the other row. And then we do something like y1 z2 minus y2 z1 for the first entry. And then we sort of rotate cyclically. z1 x2 minus z2 x1. And then x1 y2 minus x2 y1. That's really a cross product to give the normal. So the normal found by computing a cross product. So that's the definition, we could say. It's the definition of the join of 2 projective points. And it's a line. Okay, we need now a corresponding definition of the meet of 2 lines, which is the other basic operation in projective geometry. So we've had join, and now we have the meet of 2 lines. So we have 2 lines in the planar view. Maybe I'll use capitals for them. So maybe L1 and L2. And then where they meet, that's going to be a point. And that point will be called L1, L2. We're going to use exactly the same algebraic notation. The product of 2 lines means the meet, or the intersection of those 2 lines. Okay, so we need a formula for that. So if the lines are, let's say the first one is L1, M1, N1, and the second one is L2, M2, N2, then what's going to be their meet? Well, it helps again to think geometrically back to the original three-dimensional space. Okay, so this first object is really, in some sense, really a plane through the origin. So it's some plane through the origin, and its name is L1. And we know what its normal vector is. Its normal vector is L1, M1, N1. And then we have a second plane, L2, which has its normal vector, L2, M2, N2. So these two subspaces, two-dimensional subspaces of three-dimensional space, these two planes passing through the origin. And what we're interested in is where do they meet? Well, they will meet along the common line, which is also a one-dimensional subspace. So there'll be a common line. Let me draw it like that. And I want to write down what that line is. Well, if this normal is n vector n1, and this one is n2, then this common direction will lie in both planes. So it will be perpendicular to both n1 and to n2. So it must also be given by the cross product of n1 and n2. So the direction for this is just n1 cross n2. That's the direction of the line of intersection of two planes. So the formula is really the same formula as for the meet of two points, except that now we're getting a point. So we're getting a row vector, not a column vector. So we have to do the same business. So m1 n2 minus m2 n1, first entry. And then we have to rotate everything cyclically, just like we did there. So m's go to n, so n1 L1 minus, no, n1 L2 minus n2 L1, and then L1 n Lm, n1 L1 M2 minus L2 M1. All right, so that's where projective geometry starts. So we could have started off projective geometry now in a quite different way. We could have said, forget about three-dimensional space. Okay? What a projective point is, it's just a row vector, a projective row vector. Forget about what it means. It's just a triple of numbers enclosed in square brackets where we agree that if we multiply by a non-zero scalar, it doesn't change. And we could define a projective line to be a column vector, projectively. And then we could have defined the product of two points to be the line, given by this formula, and the product of two lines to be given by the point, which is this formula. Then the interpretation of thinking, well, it has one-dimensional subspaces, two-dimensional subspaces, that's not really necessary. In particular, it shows that there's a complete duality in this theory between points and lines. They're really completely symmetrical. There's a fundamental duality in this subject between points and lines. That means if you have any theorem concerning points and lines, then if you replace the points with the lines and lines with points, you get also a valid theorem. There's one more thing that we need to really establish algebraically the relationship between points and lines, and that's incidence, and maybe I'll write that here. So we need to say what's the relationship between points and lines? Okay, so the definition is that the point, okay, let me write, okay, I'll write capital X. The point at capital X, Y, Z, let's call it P, and the line L equals LMN are incident precisely when Lx plus My plus Nz equals 0. Or in terms of matrices, when the vector P times the vector L, matrix product of that 1 by 3 matrix with that 3 by 1 matrix is 0. And we have a few other ways of saying that. So if P and L are incident, we say that P lies on L, or we say that L passes through P. That's our just other ways of saying the same thing. Yeah?
So that's just the dot product?
Just the dot product. Just the dot product, because that's our original formula for the equation of the plane. That was the actual connection between the points and the lines to begin with. Okay, so we've got these very pleasant setup. We've got points and lines. We have the notion of joins and meets and incidence. And now there's this lovely duality, but we can see there's a symmetry in the subject. Okay, so whenever we have a theorem, we can have a dual theorem that's obtained by interchanging points and lines. So let me give you an example of that. So the first theorem in projective geometry, and the most famous theorem in projective geometry, is Pappus's theorem, which says that if you have two lines and you have 3 points on the lines, let's call them 1, 2, and 3, and let's say 1 prime, 2 prime, and 3 prime, just for simplicity, that if I join the 1 and the 2's and the 1's and the 2's, I will get some point. If I join the 2's and the 3's, I will get some point. If I join the 1's and the 3's, I will get some point. And the theorem, due to Pappus, around 300 years after Christ, is that those 3 points are collinear. All right, this is Pappus's theorem. It's the first and most important theorem in projective geometry. So what would the dual theorem be? So the dual result would be that instead of having 2 lines, we have 2 points. That's the starting thing, right? And then instead of having 3 points on each one of these lines, we have 3 lines incident with each one of these points. Line 1, line 2, line 3. Let's call them 1, 2, and 3. And then over here, there's some other more lines. 1, 2, and 3. Okay, 1 prime, 2 prime, and 3 prime. Okay, what did we do over here? We joined 1 and 2 prime, and 1 prime and 2. We got 2 lines. So over here, what we should do is we should meet 1 and 2 prime. Let's see if I can do that. So there's 1 and 2 prime. There's the meet there. And also 2 and 1 prime. There's 2 and 1 prime. What did we do with those 2 lines? We took their meet. So over here we should take the join. So that's exactly corresponding to finding that first point. Okay, and now we should do the same for 2 and 3. So where 2 and 3 prime meet, 2 and 3 prime meet, okay, way up there somewhere. And 2 prime and 3 meet. Which one was 3? That was 3. And 2 prime, okay, 2 prime and 3, they meet way down there somewhere. Okay, so their join is going to be, okay, some line way out here somewhere. And then the third one was where 1 and 3 prime meet, and 1 prime and 3 meet. So where was line 1? That was line 1 and line 3 prime, I guess down here. And 3 and, which one was 3? That was 3. That was 1, that was 2, that was 3. 3 and 1 prime, that's this one here. So the other line is there. So the corresponding statement here is that the 3 points that we obtained are all collinear. The corresponding statement over here would be that these 3 lines that we've just constructed are concurrent. You go up far enough where they do meet, they all meet, all the 3 lines meet at one point. So that's the dual of Pappus's theorem. And it's an automatic consequence of Pappus's theorem and this formulation of projective geometry, which means that everything is completely symmetric. That's the dual result.
If we've got these lines that you produced by Pappus's theorem, they're not the same as like a one-dimensional subspaces because they're all obviously concurrent because they don't have to go through zero.
Right, so when I draw a picture like this, a two-dimensional picture, I'm always drawing a picture in that viewing plane.
Okay, so
Yeah, so because I throw away the three-dimensional picture and I just show you the two-dimensional viewing plane picture. So when I say a point, it's really, I draw a single point.
at some point at some z.
Yeah, it's where you can think of this one-dimensional subspace, but it's where the one-dimensional subspace comes through and meets our viewing plane. That's our point. We have 1 point here, and then the line is the line joining them. But that line is really the two-dimensional subspace, if you want, in the plane that you get in the three-dimensional story. Okay, so the theory that we've outlined so far already has a lot of applications to two-dimensional graphics and video game construction and so on. So let me outline why that might be. So suppose you want to make a lot of computations in just ordinary two-dimensional, in the two-dimensional plane. Okay. So for example, suppose that we have some points. There's the point 4, 1, and here's the point 8/3, 24, say 27ths. Okay? And suppose for some reason we need to find the equation of the line that joins them. Okay, you learned how to do this in high school. So here's now a more sophisticated way of writing down that equation. What you do is you say, okay, instead of working with this point, I'm going to work projectively. This point is really the same as the projective point 4, 1, 1. I just tack a 1 at the end. And this point is really the same as the projective point 8/3, 27s, 1. But because, no commas. But because I'm working projectively, I can multiply this by any scalar and it stays the same. In particular, I can clear fractions. I can multiply by 21 and say this is the same as 56, 60, 21. So already we see a major advantage, and no commas. Already we see a major advantage that we can clear fractions because we have this extra coordinate that can absorb denominators. So we can do integer arithmetic instead of having to do fractional arithmetic. Okay, so how are we going to find the equation of this line? We're just going to take the cross product of these two things. All right, so the line L is, okay, it's going to be, what are its coefficients? You just take the cross product. So 60 times 1 minus 21 times 1, etc. And let's say for this, whatever it is that we get, L, M, and N, okay, I could do it, but I'm not going to, then the corresponding line is LX plus MY plus n equals 0. Right? That's how we convert a column vector like this to an actual equation of a line. Similarly, if you have two lines, if you have a second line, which is given by another equation, let's say 3x plus 4y minus 5 equals 0, and you want to see where these two lines meet, forget about solving equations. We're just going to compute a cross product again. We just write this line in our form 3, 4 minus 5. And then we take the cross product between this one and whatever this one was as a row vector. Okay, so then this point, let's call it P, would then be the row vector, which is, okay, it's 3, 4, 5, 3, 4 minus 5, across, if I like, L, M, N, as a row. So the basic computations of joins and meets are all just cross product calculations. So once you get your little routine going for a cross product, you just invoke that routine whenever you need to do one of these calculations. Okay, there's a lot of other advantages in thinking about geometry in this projective setting, and so next time we're going to talk about some more advantages, but we're also going to start looking at the parabola and curvature from this sort of projective point of view to help us. So I'll see you then.